So first of all, I'm going to touch a little bit on the intro. Let's have a little bit of recap on FFT. We all should already know that FFT is an algorithm used to compute the discrete Fourier transform, which provides speed increase factors. This algorithm is proposed by Cooley and Turkey back in 1965. It makes use of the symmetry and periodicity properties of twiddle factor to efficiently reduce the DFT computation time. It is based on the fundamental principle of decomposing the computation of DFT as a sequence of length n into successively small DFT. FFT is used in digital spectral analysis, filter simulation, autocorrelation, and pattern recognition. Next, there are basically two types of FFT algorithm, which are classified as decimation in time and also decimation in frequency. However, our group will only focus on DIT. Decimation in time means to break something into parts, while DIT algorithm is to divide or to split the sequence xn to smaller sequences in time domain. For the Radix 2 DIT FFT, the n will be basically depending on the endpoint. For example, if we are computing at point DFT, then the n will be equal to 8 here. Then R is the radix, or we can call it as base. So radix 2 will always have 2 as the R, and this L here represents the number of stages in FFT algorithm. Hence, for at DFT point, we will have 3 stages in FFT algorithm. 3 stages. So from here we can see that the endpoint is divided into n over 2 point sequences where we have 2 signals of 4 samples, which will consist of even and odd number. The process will be continued until we are left with 2-point DFT. There are 3 properties of twiddle factor in FFT. For the first one, we have Wn to the power of k plus n equals to Wn to the power of k. While for the second twiddle factor will be Wn to the power of k plus n by 2 will be equal to negative Wn to the power of k. For the third one, we will have Wn to the power of 2k equals to Wn by 2 to the power of k. For the Radix 2 decimation in time FFT algorithm, first, we should let xn be the input sequence with length equals to n. For the decimation in time, xn is split into 2 parts, which are the even and the odd part. The even index will be gm equals to x to m, where m will be equal to 0, 1, until n by 2 minus 1. For the odd index, hm it will be equals to x 2m plus 1, where m will be 0, 1, until n by 2 minus 1. Then we can write it as xn equals to gm plus hm. So now, according to the definition of DFT, we will have xk equals to the summation of n equals to 0 to n minus 1 xn wn to the power of kn, where k here will be equal to 0, 1 or n minus 1, and the wn will be equal to e minus j 2 pi by n. So according to the previous equation, xn equals to jm plus hm, so our xk equation here will be written as we will have the even part and also the odd part. And now we will replace the n on the even side with 2m, while the n from the odd side will be replaced by 2m plus 1. Then we will replace the x2m with gm and x2m plus 1 to become hm. And then for now that here the k2m plus 1 will be split into w to the power of k2m and also w and k. So as the w and k here does not depend on the m here, so we move this to be put outside of the summation. And so for now that the previous equation will become like this, where wn to the power of k is brought to the front of the summation here. And next, considering the third twiddle factor here, the 2k will become k and the n here will be n by 2. Same for the odd side here. So for now, the equation will become gk and hk respectively, where basically it is the n over 2 dft of gm and hk. So xk will become gk plus wn to the power of k hk. The n by 2 point of gk and hk are periodic with n by 2 period, so that we are able to write gk plus n by 2 equals to gk, and according to the properties of dft, it is the same thing for hk. However, according to the second property of twiddle factor, which is wn to the power of k plus n by 2 equals to negative wn to the power of k, if xk equals to gk plus wn khk, then it will become xk plus n by 2 equals to gk minus wn to the power of k.
Now we study about technique of Radix to decimation in time DIT FFT algorithm. Butterfly diagram. First we have GK and HK, and the addition of GK and HK is added, as GK is directly added to the HK multiplied by W n power of k, and the result is XK. For the bottom part, where HK is multiplied with negative W n power of k plus with the gk, and the result is x k plus n over 2. And from this thing, you can see that the diagram is look like a shape of butterfly. Therefore, this diagram is set as a butterfly diagram. First stage of decimation at point FFT. Now we take xn data, x0, x1, x2, x3, x4, x5, x6, and x7. First, we split it into two parts, that is even and odd sample. which is Hm and Gm respectively. For Hm, that is even sample, we have X0, X2, X4 and X6. For Gm, odd sample, they are X1, X3, X5 and X7. Now we compute 4-point DFT of Hm, and we got for Hk sequences are H0, H1, H2 and H3. And 4-point of DFT of odd sample are G0, G1, G2, G3 and this sequence named as GK. After that, we just add as butterfly diagram with some Hk sample and Gk sample. H0 from Hk plus G0 W n power of 0 from Gk sample. Again, H1 added with G1 into W n power of 1 and the result is X1. The operation is same for X2 and X3. Next, for sample, G0 multiply with negative twiddle factor, that is H0 minus with negative W4 power n into G0 and the result is X4. Same goes with X5, X6 and X7 with different twiddle factor, that is negative Wn power 5, negative W6, negative n power 6 and negative Wn power z. This same idea can be applied for calculating n over 2 DFT of the sequence Gm and Hm in above case 4-point. It can be obtained by splitting again Gm and Hm into their odd and even index sample. This idea can be applied recursively log base 2 power of n time if n is power of 2. If n is equal to 2 power of v, then the final stage sequence are all of length 2. For a 2-point sequence, xn is equal to x0, x1. The DFT is like xk n is equal to 0 to 1 summation of xn w2 to the power of kn. x0 is equal to x0 w2 to 0 plus x1 w2 to 0 is equal to x0 plus x1. x1 is equal to x0 w2 to 0 plus x1 w2 to 1 is equal to x0 minus x1. If we find the 2-point DFT, then we get a diagram like this. From this we can notice that we can easily calculate 2-point DFT as the frequency domain sequence are first one summation of 2 time novel sequence and the second one are subtraction of 2 time domain sequence. For 8-point DFT, we split the xn into even and odd part Gm and Hm. Now for 4-point DFT, we split Gm and Hm into their even and odd part. P1L and P2L contain even and odd part of Gm respectively. That means Gm is equal to P1L plus P2L. Q1L and Q2L contain even and odd part of Hm respectively. That means Hm is equal to Q1L plus Q2L. Next, we draw the pictorial view of splitting the index of xn. Xn consists of x0, x1, x2, x3, x4, x5, x6 and x7. First we take even sequence of xn index and its name as Gm. They are x0, x2, x4, x6 and odd sample, that is Hm, and consists of x1, x3, x5 and x7. Then again we split the Gm to even part and odd part. Even part named as P1L and G0 which is x0 and G2 which is x4 are the even sample, and odd part P2L, G1 and G3 that is x2 and x6 respectively. HM also divide into even and odd part. Even part named as Q1L and the sample is H0 which is x1 and H2 which is x5. Odd part Q2L sample that are x3 and x7. This is the pictorial view of splitting the index value of xn. It showed that for n is equal to 8, initially input sequence like that: x0, x1, x2, x3, x4, x5, x6, and x7. The first split required the data to be arranged as follows: x0, x2, x4, x6, x1, x3, x5, and x7. In the second and final split, the data appear in the following order: x0, x4, x2, x6, x1, x5, x3, and x7. Final representation of 8-point FFT. We take 8-point sequence of xn that are x0, x1, x2, x3, x4, x5, x6, and x7. According to the bit reversal method, the sequence is shown as x0, x4, x2, x6, x1, x5, x3, and x7. Here, the n is equal to 8. Thus, there will be 3 stages because n is equal to 8. Mean that 8 is equal to the 2 to the power of 3. So the number of stages will be 3. So here we compute 2-point DFT between x0 and x4. Same for x2 and x6, x1 and x5, and x3 and x7. Here we compute 4-point DFT and we get 8 output. In second stage, first 2 output taken are the same and third and fourth output multiply with Wn to the power of 0 and Wn to the power of 2 respectively. The operation is continued by multiply the third and fourth output with -1. Now here we use butterfly addition. First 2 output added with second 2 output of x2 and x6, and second 2 output added with first 2 output of x0 and x4. Same thing happened with bottom 4 output. And the third stage, first 4 output are no change. However, next 4 output multiply with Wn to the power of 0, Wn to the power of 1, Wn to the power of 2, Wn to the power of 3, and as well as multiply with -1 before addition. As usual, we use butterfly addition where first 4 output of second stage added with bottom 4 output multiplied by -1. Next, continue by multiplying the bottom 4 output with first 4 output. Therefore, the results are x0, x1, x2, x3, x4, x5, x6, and x7. We can see that in first stage, we compute 2-point DFT and apply butterfly addition. Same goes to the second stage and third stage where we apply butterfly addition to obtain the output. Thus, this is the final representation of 8-point FFT.
Now let's see an example of 4-point DIT FFT question. Given the Sn is equal to 0, 1, 2, 3. So find the Sk using DIT FFT algorithm. So first we can see that we need to construct the flow graph for the DIT FFT. So first we can see that there is 4 number in the Sn. So we assume that n is equal to 4. So first we need to use the bit reversal process to identify the sequence of the flow graph. So since that n is equal to 4, 4 is also equal to 2 to the power of 2. So we use the 2 bit to represent that. First we can see that 0, 1, 2, 3 with the two binary form particularly. First 0 is equal to 0, 0, 1 is 0, 1, 2 is 1, 0, 3 is 1, 1. So after the bit reversal, we can see that the number is reversed. For the 0 is unchanged because it's 2 0. So for the 0 1 it changed to 1 0. 1 0 changed to 0 1, and 1 1 also remain the same. So the new sequence is appear. First is 0, 2, 1, 3. Next. So firstly, we also need to arrange it like this. You can also use the way that to identify the even number and the odd number. There are two ways. Next, first, through the introduction of the DITFT, you know that there is a basic flow graph pattern. So firstly, it will cross one time each other, and then next, it will cross again to the like. For the first one is 1 and 2 cross, 3 and 4 cross, and the second part is 1 and 3 cross. You can see that 1 and 3, this line. The second line, you can see that 1, this one is 2, 4. For this 3, 1. For the 4, 2, like this. So next, this is the full flow graph for the 4-point DITFT. Here is SN 0213, and here is SK 0123. So first, we need to calculate at the first part for the line 1 and the 2. Answer is using its particular input number. Okay, 0, after that plus 2 is equal to 2. Next is using the line 2 with line 1. So 0 plus minus 2 is equal to minus 2. So next is using the line 3 and line 4. 1 plus 3 equal to 4. After that, for the line 3 and line 4, you can see that 1 plus minus 1 minus 3 equal to negative 2. So here is, we finish the first part. After that, we'll go to the second part. We need to do it separately to make it easier. So first line and third line, 2 plus 4 is equal to 6. Next, line 2 and line 4. Negative 2, here is minus 2 multiplied by minus j, so it is equal to plus 2j. So next, line 1 and line 3. So first, the first line is equal to 2. After that, the third line is multiplied by 1 and multiplied by negative 1. It will become negative 4. Therefore, 2 minus 4 is equal to 2, negative 2. After that, we'll go to the last line, line 2 and line 4 is negative 2 for the line 2. After that, plus negative 2 multiplied by negative j multiplied again with negative 1 is equivalent to negative 2z. Therefore, the line 4 is equal to negative 2z minus 2. Therefore, this is all the value of the sk. Thank you.
Now, I would like to talk about at-point radix to fast Fourier transform decimation in time. Let us see one example here. So the question for radix to fast Fourier transform can be asked in two ways. Find the at-point discrete Fourier transform of the sequence xn using radix to DIT-FFT algorithm, or compute the DFT for the sequence using DIT-FFT algorithm. Given that xn is equal to this, so we can indicate that x0 equal to 1, x1 equal to 1, and so on, until x7 equal to 0. So firstly, we need to determine the length of FFT, which is capital N. So as given in the example, we have to determine the at-point DIT FFT. So N equal to X. Next is find the phase factor of W at to the power of K. To find the phase factor, we need to know the Euler's formula as shown here, especially for the first equation here. The phase factor Wn to the power of K is denoted by exponential to the power of negative j2 pi k over n, where n equal to 8, then k is 0 until 7. So we use the Euler's formula to find W0 until W8 to the power of 7. For at-point DIT-FFT algorithm, we will require 4 Twiddle factors. The first Twiddle factor we require is W8 to the power of 0 with the value of 1. Then the other 3 Twiddles factor are W8 to power of 1, 2, and 3. The next step is to decimate the input sequence by using the bit reversal process. The input index for the at-point DIT-FFT is 0 until 7. So for the second column, we have to determine the binary bit index. For 0, the binary bit index is 0, 0, 0. And for input bit index 1, the binary bit index is 0, 0, 1. For the third column, we have to reverse the binary bit index, as shown here. Now we have to write the bit reverse index. So for 0, 0, 0, we will get x0 equal to 1. And for 1, 0, 0, we will get x4 equal to 1, and so on. After that, we need to draw the butterfly diagram. Computation of at-point DFT using Radix to FFT involves 3 stages of computation: stage 1, stage 2, stage 3, as shown in the diagram. So, to draw the first stage of butterfly diagram, whatever the reverse bit are, we write here. x0 equal to 1, x4 equal to 1, x2 equal to 1, until x7 equal to 0. The 2 points here are the summing points. Next, we need to apply negative 1 at the bottom line of the 4 butterfly structure. Besides, we also need to apply the first Twiddle factor W at to the power of 0 equal to 1 at the bottom line of the butterfly structure. To calculate the first stage output, the first line is 1, then the second line is 1 multiplied with the Twiddle factor 1 equal to 1. So we do the addition at the summation point here, so the answer will get 2. Similarly, we have this output 1 here plus this output 1 here multiply with negative 1, then we will get 0. We will do the same step for the rest of the 3 butterfly structure. So these are the outputs at the first stage. Then we need to draw the butterfly diagram for the second stage. For the second stage, we will have a bigger butterfly structure as shown here. In this case, we need to apply the summation sign at these points. Next, we need to apply 2 negative 1 at the bottom line of the butterfly structure. And we need to apply the first and second Twitter factor at the bottom line, which are w add to the power of 0 equal to 1 and w add to the power of 1 equal to negative j. We have to calculate the second stage output based on the first stage output that we have found just now. To do the first addition at the first summation point, we have this output 2 here plus this output 2 here multiplied with the Twitter factor 1, we will get 4. Similarly, for this first stage output equal to 0 plus this 0 multiplied with the Twitter factor negative j, we will get 0. Then we continue to do the rest of the summation. For the third stage of the butterfly structure, we need to apply 4 negative 1 at the bottom line. Then we also need to apply the 4 Twitter factors at the bottom line of the butterfly structure. We have to calculate the third stage output based on the second stage output that we have found just now. At the final output stage here, we are getting FFT. This FFT have the natural sequence order x0, x1, x2, x3 until x7. After doing the addition at the third stage, this will be the final output. So here we call this is the FFT of the given sequence.
Let's try another example. Compute the FT of the given sequence using time decimation FFT algorithm. First of all, we label the given sequence with numbers from 0 to 7. Instead of using bit reversal process, we can find the input sequence simply by dividing x of n into even and odd numbers. For the even numbers, we have x of 0, 2, 4, and 6, while for the odd numbers, we have x of 1, 3, 5, and 7. Again, divide it into even and odd parts, and we have 0, 4, 2, 6, 1, 5, and 3, 7. Finally, we get the input sequence and x value by referring to the given sequence of xn, where x of 0 equals to 1, s of 4 equal to 4, s of 2 equal to negative 1, and so on. Before we do the calculation, we have to draw the butterfly diagram. First, draw a parallel line and label it with the input sequence x0, x4 until x7. The 3 columns here represent 3 stages in butterfly diagram, and this is the connection of line of butterfly structures in each stage. Then include the Twitter factors and label negative 1 at the bottom half of the butterfly structures in each stage. Now we have to insert the value of the input sequence where x0 equal to 1, x4 equal to 4, and so on until x7 equal to 2. In order to find the output value at the summing point here, we have to add the values of the line. As for this point, 1 plus 4 equal to 5. And this value here, we have to multiply with negative 1, which results in negative 4 plus 1 is negative 3. Negative 1 plus negative 1 is negative 2. Negative 1 into negative 1 is 1. 1 minus 1, 0. 2 plus 2, 4. And 2 into negative 1 is negative 2 plus 2 is 0. 2 plus 2 result in 4, and 2 into negative 1 is negative 2 plus 2, 0. The output of stage 1 is use as the input for stage 2. As for stage 2, if there is a triple factor, we have to multiply it with the output of stage 1. So for this one, we know that W add to the power of 0 is 1. So 1 times negative 2 is negative 2 plus 5 is 3. And this one is 0 minus 3 is negative 3. And then negative 2 into negative 1 is 2 plus 5 is 7. And 0 minus 3 is negative 3. For this one, 4 times 1, 4, and then plus 4 is 8. 0 plus 0 is 0. And then 4 into negative 1 is negative 4 plus 4, 0. And 0 plus 0, 0 here. And then we continue with stage 3. 8 times 1 is 8, plus 3 is x of 0 equal to 11. And then this one is 0 minus 3 is negative 3, and then 0 again plus 7 equal to 7. And then 0 minus 3, negative 3. And for this one, add into negative 1 is negative 8 plus 3, we have negative 5. 0 times negative 1 is 0 minus 3, negative 3. And then 0 plus 7, 7. 0 minus 3 is negative 3. And this is the output value of this question. So by drawing the butterfly diagram, we can get the final values of x of 0 to x of 7. And this is denoted by x of k.